Okay, good morning, everybody. I guess we can start. And the first thing that we want to, let me just fix the board a little better. Okay, so the first thing we want to mention is we have two vector null identities, and these null identities initially they obey to any vector definition that we have provided from the mathematical perspective. Now, it is lucky for us, it's also good for us, that electromagnetic fields, electric field and the magnetic field, obey to these null identities, which means that they, if we have defined them as being specific vectors, they have to obey these interesting properties. So, if we have, which becomes a little tricky in terms of, if you think from the bigger picture, of what a vector can do and what electric field can do, then obeying these vector identities, we are lucky that they do it this way. And these null identities, what they are, we have the curl. So here we have the del operator, the curl of a gradient of a scalar quantity. So you know what this is? This is the del operator of a scalar quantity. That's the gradient of the scalar quantity. We do also the cross product with another del operator, and that's what we get. And then the divergence of the curl of a vector. This is also zero. So here we have two null identities, and from this one here, sorry. So these null identities, we get a zero for these two, and what we can understand from here is that if we have, in the case of the electric field, it can be written as a gradient of the potential, which means that the curl of the electric field is always going to be equal to zero. So that's a null identity, but then in your background, you can always consider the following. The curl of an electric field is equal to zero. It's because of these vectors behave this way. At the same time, we see that the divergence of the curl of a vector is also going to be equal to zero. And as we are going to see in a couple of weeks from now, we are going to see that there are some vector quantities which can be written in this form. One of them is the magnetic field. Okay? This magnetic field B, we're going to see this part later, it can be written like this, which means that we can also write that the divergence of the magnetic field, this is equal to zero. Okay? So these are the vector properties that we consider them to be the null identities. And in very soon, we'll see that because of these vector quantities, also the electric and the magnetic field will obey in a strict way to these properties. So that's something we can consider for now. And in fact, if this is true, which it is, we can call that B, for this specific case, this is called divergenceless, or solenoidal. So, like a solenoid, it's a structure or a geometric figure which looks like a cylinder. So, magnetic field, that's what it is, for the sake of obeying such a vector quantity. So, these null identities, I would ask you to go over to look at these in the book, and in terms of these two null identities, any field they can be considered as solenoidal or irrotational. Okay. So they can either be S and I, where S means solenoidal, I is irrotational. And now we can 0, 1. Okay, so yeah, I can construct a matrix-like structure, which let me think how I can represent this one as best as possible. So a field can be solenoidal, but not irrotational, or so if we have these two conditions, we can have a field which is 0, 0, which means the field is not solenoidal, not irrotational. It can be 0, 1, 1, 0, or 1, 1. Okay. So for any field that can have these two properties, we could have these four possible combinations. And the irrotational, so irrotational, it's a field whose curl is equal to 0. Solenoidal is a field whose divergence is equal to 0. Solenoidal. So now for different configurations, we could have a field that is neither solenoidal nor irrotational. It's not solenoidal, but it's irrotational, or it can also be both. Now let's consider a couple of extreme cases where we can have the electric field in a charged region. Let me think for a moment. So a couple of these combinations, they look a little not as if we don't understand this very well. But we'll see in 3 to 4 weeks, we'll see that even, especially the first one, this is non-zero in the case when we have the magnetic field as a function of time. Because when the magnetic field it depends on time, it will induce an electric field because these two are coupled quantities. And especially the first expression, it will fail, and we'll see that a couple of combinations of divergenceless or the divergence character of a field, if we don't see it in a static condition, in a time-dependent condition, we are going to observe that these properties might shift. But we'll come back to these when we come to the time-dependent regime, where the electric field and the magnetic field are coupled in a much easier way. Now, from the last time, we have covered the Stokes Theorem and Divergence Theorem, and now we're going to move to we're going to start and derive the laws of electrostatics. And regarding the laws of electrostatics, as we have promised, we have said that we are going to derive everything from the postulates. The first postulate for the electric field is that the divergence of electric field is equal to the charge density rho over epsilon 0. So that's the first postulate. And then the second postulate is that the curl of E is equal to 0. Okay, so that's all. We start discussing the electric field just by assuming these two to be true. Okay, and nothing else. Which means that sorry, let me just set this. So assuming these two, let's see first of all what we have here. This rho, this is units of Coulomb per meter cube. Epsilon 0, that's the permittivity of free space. And the second equation, there is not much to say about it, but we just say that this electric field is irrotational. So this matches this definition. Okay? This in the time-independent regime or time-independent domain. So starting from here, we can, or starting from the first, null identity, allow me to raise the unit of the O, which is Coulomb per meter cube. We can, if you remember, we had the Divergence Theorem and the Stokes Theorem, where the Divergence Theorem, it was written like this. So we have the divergence. In this case, let's consider the electric field to be the field of interest. So this, if we integrated this one over volume, this should be equal to the E dot ds. So the integral over 3d is equal to the integral over 2d, or integral over meter cube. This is equivalent, not equivalent, but by doing a small change, this will be equivalent to the integral over meter squares. That's how we consider that. And then what we can say from here is that from the first part that we observed in here, we can write that instead of this term, we can write the rho over epsilon 0, integrating over a volume. This is going to be equal to, and if we look at this side, this is a closed integral, which means that this is the flux. So last time, we just mentioned for a moment, we said that the surface area integrals, or let me write it like this, surface integrals, for the sake of this course, they are equivalent to the flux integrals, okay? As if you are calculating integral, which means that if we are calculating the surface integral of a vector field, we are calculating the flux. And the definition of the flux is defined as a certain area times a vector field that is pointing perpendicular to this one. So if we have a field which is going like this, we have a non-zero flux. But if the area is right here, and the vector field is going at such an angle, then the flux here is going to be equal to 0. We also know that the surface areas of interest, they are defined by a normal vector to that surface area. So in this case, if this is the x-axis, that's x, and if this is the y-axis, then using the right-hand rule, the z-axis is going to be in this out of the board. Okay, so this will be the z-axis, allowing to denote this one with a point coming out of the board. In this case, this surface area element that we see here, the area, which is a vector, this is equal to the magnitude, which is area, times a z. Okay, so this is a vector quantity, and we need to include the magnitude and its direction. So in this case, the flux, which is this integral here, if the electric field, if the field of interest is, let me allow to get to some more space. So if the field, let's say the first case, if E is equal to 3ax plus ay minus 2az, okay? So let's assume that we have such an electric field, and the question is, let's find what is the flux of this electric field over this area. In order to find the flux, so the flux, we can denote it like this, for the sake of getting used. So sometimes I might write this in the board also like this. This is equal to the integral over the area of E dot ds, or the area itself. So in this case, this is going to be equal to 3ax plus ay minus 2az, and then we take the dot product of this one with this element, which is aaz. So in this case, the dot product between of these terms, it will be null. So it will be 0, because we know that the only term that survives is going to be this minus 2a, okay, in this specific case. So again, this was just a small reminder of how we calculate the surface integrals. Now let's come back to the divergence theorem, which we have here. In this case, this is, we can write this one. So surface integral is a flux integral, and this EDS, this is going to be equal to the, let's assume that this is the flux, and then we come here at this part, this permittivity of free space, it's a constant. So we can take this one out of the integral, and if we do that, we just will have the 1 over epsilon 0, the integral of rho dV. This is equal to the flux. Then, just for a moment, we can have a look at the units of this integral. So the rho is measured in coulombs per meter cube. The volume is meter cube. So if we multiply these, it looks like the outcome, it will be a charge. Okay, it will be coulomb. So overall, it looks like here we're going to have the charge divided by epsilon 0. This is going to be equal to the flux. Okay, so it looks like a great simplification of the flux of a certain charge. So, and this is also equal, again, I think this is enough, but we can also consider the following. So any E dot ds, this will be the definition of the surface area, will be equal to this expression, Q over epsilon 0. Then we can erase this null identities. So the null identities are gone, but let's keep this for a moment. So we claim that that's all we need to derive the laws of electrostatics. So now, for a moment, let's assume, but let's first see what this expression teaches to us. This tells to us that if we have a charge here, Q, and then if we have a surface area here, S1, the flux over the surface area S1 is equal to Q over epsilon 0. Okay? And then if you have another surface that extends like this, which will be S2, this surface also, sorry, if you cannot see the board, please just tell me. I hope I can hear you. So the flux over the surface S1 is equal to the flux on the surface, so let me write it like this. Flux over S1 is equal to the flux over the surface S2. So the shape of the surface area, it does not have any effect on the flux. And in order to remember better what the nature of flux is, we can say that the flux, it is equivalent to the number of field lines on the number of field lines over a certain area. So if it is the number of field lines, this should be independent of the area under consideration. So now, and let me also say this one, that the flux as a quantity is much more essential than the intensities, electric field intensities. So if a quantity is much more important, or if it has a higher rank of hierarchy. So I can write this one, the flux, it has a higher rank. So if you need to derive any equation or any rule, using the flux is much more essential. Then, sorry, okay. So let's move on for a moment. Let's assume that we have a charge Q here, and let's consider a surface area which goes like this. But for the sake of having an easier task for us, let's not consider the surface area in red, but let's consider a spherical area around this cube. And then let's try to identify let's see what we can derive based on this rule here, which the rule stated that Q over epsilon 0, this was equal to E dot ds. So, first of all, we know that the electric field from a positive charge, it will be positive, it will point like this. So this is a constant value, and this electric field, it will have a direction which is in spherical coordinate system, this will be AR, okay? Just as a reminder, in spherical coordinate system, we have R, theta, and phi. So if the electric field is pointing out of this spherical area, that's what we get, then we take the dot product with this ds. So the dot product with the ds is going to be equal to, so first of all, what is ds? ds, if we look, ds, it should be equal to, let me think for a moment. How can we derive the, let's take this out. In spherical coordinate system, the d volume, it's equal to dr, then we have r d theta times r sine theta sine theta d phi. So this is the d volume. If this is the d volume, if we fix with a constant r, the surface area element ds, it's going to be equal to r squared sine theta d theta d phi. Okay. So this is the surface area element. If we consider also that there are vectors, if we put here a vector sign, this will be this quantity, and then we have to multiply with the vector which is perpendicular to the sphere. And the vector perpendicular to the sphere, we just multiply here with AR, A capital R. And my board is becoming a little challenge to read, but let's have a look here. So this is a ds. So if we include all of these terms in here, I don't want to erase the divergence law. So if we multiply this with this term, so let's assume that this is dsAR, capital R. AR with AR, they are in the same, the angle between these two is 0, so we get 1. So then in this integral, we'll simply have the integral of E times R squared, whatever the R is, sine theta, d theta, d phi, and the integral, it has to be from 0 to pi for the theta, and from 0 to 2 pi for the phi. So if we take this integral, first of all, we can see that this electric field is constant for constant R. Electric field is a constant, so we can take it out of the integral. So this whole thing can be equal to E times, and we know that the surface area, the integral over surface area of the sphere is going to be equal to the 4 pi R squared. That's what we know for here 4 pi R squared. And from the other side, we have the charge that we are considering over epsilon 0. So at this instant, we just look that this term is equal to this whole term. And if this is the case, if we equal them both, we can see that Q over epsilon 0, this is E times 4 pi R squared, and the electric field, then it's equal to 1 over 4 pi epsilon 0 Q over R squared. You know this law before. This is called the Coulomb Law, dg Coulomb, which expresses how the electric field depends on the charge. So it looks like we derived this law from the postulate of the electric field, and that postulate was this: that the divergence of the electric field was rho over epsilon 0. So from this postulate, we got this. Okay. So this is from this postulate we get this, and we also learned that we see that the electric fields it changes as 1 over R squared. So that's the first thing that we learned. Also, similarly, we can derive, so I hope this part is clear. Then from the second postulate, we can also derive something very useful for the sake of having these important laws next to each other. This was a divergence theorem. The Stokes theorem, it states that the curl of electric field over ds, this is going to be equal to the integral of E dot dl. Okay? So this is the divergence theorem, this is the divergence theorem, this is the Stokes theorem, and we try, let's see what we get from here, from the second one. And it looks at the curl of E. From the postulate of the electrostatics, it was equal to 0. So if we set here a 0, 0 dot ds, if we integrate, we get a 0. Okay? And this 0 is equal to EDL. Now, EDL, what does this mean? First of all, let's notice that for the divergence theorem, this integral is over a closed surface area. For the Stokes theorem, this integral is over a closed interval, line, across a closed line. What does this mean? First of all, let's have a look at the units of this integral. So the electric field, this is measured, is volt per meter, right? Electric field, this is volt per meter, times meters, which is the unit of L. So it looks like this is volts. So it looks like potential, which is measured in volts. This potential, this was the, oh, okay. Let me also write this one. This is Gauss Law. So I forget to remind you that this was a postulate, at least the first one. And from this postulate, we derive this, which is the Gauss Law. And from this postulate, we also derive this, which is the Coulomb Law. So it looks like it was really beneficial to work on that. But at the same time, let's look what this means for us. This means that if we go from some point, if we go from some point A, and you go across a certain path to any point B, okay, and you keep integrating the E, or measure the circulation of E over the path, E dl, then if we get some value, and in principle, this would be the potential difference VA minus VB. Then, so you go from point A to point B, then if we come in this way, then if we go backwards to point A again, following any path of interest, we find that the potential difference is equal to 0. And this really makes sense. So we start from point A, we measure the potential difference all across, we go back, and we should measure the same potential, which means that delta V, delta potential, which is equal to VA minus VA, is equal to 0. Now, what is this law? This law is a very essential law, which in circuit theory, we call this one Kirchhoff law. Which Kirchhoff law states that if we have a circuit where you have different circuit components like resistors, capacitors, or inductors, going across a closed path, you turn back to the same point, you can add up all the potential differences of all the components, and you get 0. So it looks like from these postulates, at least for now, we've got 3 new laws. We get the Gauss law here, we get the Kirchhoff law, and also we got the Coulomb law. So these are 3 very essential laws of electrostatics. Then let's move up to let's pass, and then what we're going to write right now, it's something that probably you have seen. And between the potential difference between any 2 points, if we write this one VB minus VA, this is going to be equal with the integral from A to B with a minus sign of E dot ds or dl. You know what the unit should be, because if we want to get volts here, we should also get here volt per meter times meter. We get the correct unit. So, and then if we integrate, if we do all this integral step by step, what do we? So if this is the point Q, and we want to go from point A to some point B here, and if the path, let's assume that this path, it follows here. Oh, maybe it's better. So let's assume we go from point A to point B, and this is also intersected. So we want to follow such a path, okay, from A to B. And what we want to, let's try to see what is E. E itself, it's minus the integral of K. And in the previous expression, I apologize, but maybe I did not do a good job. We had the electric field, it was 1 over 4 pi epsilon 0, Q over R squared. If this is a vector, it's best to write here AR, okay, that's the direction. But at the same time, this is called the Coulomb's constant. Okay, so this is K, Q over R squared. So probably I forgot to mention this one. So if you see a K here, that's what it is. And also this means that we can see that the different constants in nature, they are strongly related to each other. So the K, it looks like we have a 4 pi dependence. Probably this 4 pi, it comes from the fact that the surface area of a sphere is 4 pi r squared. Okay, so if we believe that the surface area of a sphere is 4 pi r squared, this 4 pi, it better appears here, okay, because it's the surface area over which we are calculating a flux. Probably, that's also a question. Why is this kq over r squared? This could have been kq, over r to the point 2.0001. This could also be true. Experimentally, it might be difficult for us to confirm which one is the best. Is this r squared or r to the power 2.00001? Probably we'll never be able to distinguish something like this here. Okay, but if we believe the surface area of a sphere is 4 pi r squared, which it is, then we can remove all the doubts. But a big question is often the question whether we need these 4 pi's here. We do, because they appear in the surface area. Now let's come back here, and we say that electric field is K Q over R squared times A R. Then we take the dot product with ds. Now, for a moment, let's assume that this ds, this has different components. So for a moment, let ds be equal to dr AR, okay, plus R d theta A theta, okay. So this is how we can write this one in different coordinate system, plus R sine theta d phi A phi, okay. So this is the unit element which is measured let me find the correct word, is an infinitesimal length vector that we can write. Sorry, this is AR. And then if we put this whole term here and take the dot product with the electric field, for sure, any dot product with these terms will be 0, because we know that the spherical coordinate system is an orthogonal coordinate system, which means that any AR dot product with A theta, this will be equal to 0. And of course, similarly, AR dot product with A phi, this will also be equal to 0. Which means that if we insert, for the sake of the mathematical operations, this whole term here, the only terms that will survive, it will be this. Which could mean the following. If we can construct this path from A to B, which is composed of regions where, or let's do it like this actually. Let's assume that we're moving in a path like this, okay? And then let's follow this path. Okay? So what do we understand from here? If we want to find this integral, this E, what is if we are moving across this path here, let's consider this point C. If we go from A to C, and so again, we are trying to decompose this path. What is EDS? EDS, if you go from point A to point C, is going to be equal to EAR, okay? Because along all of this path, electric field, it will be a vector which is going to point in this direction, right? And then the path itself, it's AR. So this is DS times, A theta. Which means that along this whole path, we are going to get a zero, because once you take the dot product of an electric field which points like this, and the path which points 90 degrees with respect to the field of interest, we should get a zero. Okay? So the integral from A to C is zero, and then the integral from C to B, let's see what it can be. To integrate from C to B of E AR times ds times AR. So we know that if we go from C to B, this is the radial distance. This is also has the same unit, same direction. So they cancel out, and we are left with E dr, where R is from RC to RD, whatever the radiuses or distances are. We also know that since this was like a circle, the radius RC is equal to RA, so we can have this one here, RA. So in using some arguments so that we don't lose the general concept because we are dealing with vectors, we can say that we are simply, what we are really doing here, we are integrating the KQ, which are constants. Here we have 1 over R squared dr. That's what we are really integrating. And this is equal to minus 1 over R. So in the end, this whole EDS, if you follow all the steps, we're going to get something like KQ 1 over RB minus 1 over RA. So that's something that we can derive for the integral of EDS, but at the same time, it's important to know, because this means that what is the potential difference? What is the potential difference that the charge will experience if it goes from point A to B? Okay, that's how much change we're going to observe. Then we can also, at this instant, we can also look at this expression. The potential is defined as KQ over R. That's important. We have another important quantity, that if we charge, if we multiply this expression on both sides with, let's say, capital Q, we get units of joule, okay? Which means that the energy, so just by looking at the units, we can say that this is joule, which immediately we can define an energy term. So that the charge Q will be this one, and we carry this one over this path. Then if we do that, that will be equal to the work done to carry a charge from point A to point B. So we can have that U is equal to K Q1, Q2 over R. This is the energy. And then, for example, let's try to we accept this one as, so all this attempt was to prove that this is correct, and then the next step that so a good example, it could be the following. So what is the work done? We bring 4 microcoulombs from infinity to R equal to 5 meters. Okay, so that's a valid question. We have let's say we have 6 microcoulombs sitting here, and we want to calculate the work done, we want to bring 4 microcoulombs from infinity. Then, to do this one, we just need to, so the work done, which we can write as W or U, because we wrote this energy in this term, this will be equal to, oh, we can derive this one in a couple of different ways. First of all, we can just say, do the following. Let this be Q1, let this be Q2. So this will be the charge of Q2 times the change in potential, which is created by the Q1, or this can be equal to the force between the two charges times dr. We know that the work is equal to force times distance. So in this case, the force will be equal to K Q1 Q2 over r squared dr. If we integrate this, we'll get a similar expression when we do the following. So this is Q2 times K Q1 over r. Okay, so we get very similar expression whether we do the potential difference or whether we integrate the force. Now, let's from here. So I think this part is clear, and as a result, the energy to construct this system would be equal to K Q1 Q2 over r. Or here, this RD, in this case, it will be infinity minus 1 over RA, which would be 1 over 5 meters, okay? So this previous integral that we just solved, we can substitute the values here. The K, it's something like, I guess it's something like 9 times 10 to the power 11. I hope, no, it's 10 to the power 9. I don't remember, let me see if I have it in the notes. It's 9 times 10 to the power 9. 9 times 10 to the power 9. It's another constant which is to the power 9 times, this is 6 microcoulombs, and this is 6 times 10 to the power minus 6 times the other charge, which is 4 times 10 to the power minus 6, 4 microcoulombs, divided by 5 meters, and here we get that the energy of the system, it's 9 times 6, 9 times 6 microcoulombs times 4, divided by 5, and here we have 10 to the power 9, 10 to the power minus 6, 10 to the power 3. Overall, we get 10 to the power minus 3. So then, if this 6 times 4, it's 20. This is 24 divided by 5. This is approximately 5. This is approximately 45 times 10 to the power minus 3. Now, this is the energy which is accumulated in the system if we have two charges. Now here we have an important conclusion that we can make. So we have this charge Q1 sitting here. Then we bring another charge Q2 from infinity. Okay? And the distance between these is 5 meters. Now the work that we do to bring this Q2 from infinity to here, it's also considered to be the energy of the system. So we can say this one in different ways. So the same way that if we raise a certain object from the ground to some height, the energy of the system is mass times g times h, mass times the gravitational constant times the height. So how much work did I do to bring this one up? mgh, good. That's also the energy of the system. At the same time, how much energy did I spend or you spend to bring this one from the infinity? It's equal to the work done, or it's also equal to kq1 q2 over r. Okay, that's the energy or the work done. Now, for a moment, we are also doing an approximation here, and the approximation is the following. These are point charges. Okay, these are not charges that are extended in space. To be extended in space, this would be a charge which looks like this, and probably the potential energies might be a little different to integrate over to find the total energy of the system. But the moment that these are point charges, the forces are always defined like so. The force, it will be simply defined like this: K Q1 Q2 over R squared. Okay, if that's the case, that's good for us. We can keep this one. Otherwise, we need to integrate. So here we have a small change or a huge change between having point charges and the charges extended over some volume. And regarding this, we can even ask a question. Well, the question, we can ask it in two different ways, but they have the same solution. So I want you to think for a moment. Imagine that we have something like this, which we call it Earth. So if someone asks you how much work was done to create the planet Earth, okay? The first thing that you have to consider is what is the force that keeps these things together? That's the first thing to ask. Probably it's gravitational force, okay? And then let's ask also, so Earth has a radius which is like 6,000 kilometers. This is 6 times 10 to the power 6 meters. That's the 6,000 kilometers. You go from here to Germany, it's 2,000 kilometers. Let me think for a moment. 3 times, if you drive 3 times that, you go to the center of the planet Earth. Okay, it's not that big, like a small stone. Now, the same question can be asked if we have a charge which has a radius of 2 meters, but it's a material which is completely charged. Okay, so this has coulombs. So here for Earth, we have gravitational force. Here we have electrostatic force. So the solution for both of these problems is the same, but the solution to what? What was the question? The question was how much energy, or how much energy does this system have, or how much work was done to put the Earth together? Okay, if we put pieces of Earth, of mud together, and we can construct how much we get stones and everything, how much work we do to construct this, and how much work do we do to construct this if these were charges, which means that here we have some charge, then the next layer we have some more charge, then the next layer, of course, it goes on like this. So to calculate the work done to construct either the Earth, which is made of gravitational force, and the gravitational force is similar because it's equal to G m1 m2 over r squared, and the electrostatic force is K q1 q2 over r squared. So they are very similar. But now this is how we pose the question, and the solution it looks something like this. We have this force, and not this force. So we use the same idea, like we bring one charge from the infinity. In this case, we'll assume that initially we have some charge at the radius r, okay? And the charge here is q. Then we bring an infinitesimally small amount of charge from the infinity, which has a thickness, which is, the amount is very small. Let me draw this in red. And the question is, how much work do I do, or does one person do, when we have a charge q already standing there in black q, and we bring another charge which is dq. First of all, the dq, we can write this dq as the charge density rho times 4 pi r squared dr, okay? The unit volume element in a spherical coordinate system, this is what it is the surface area of the sphere times the thickness, okay? So this is the dq, and the work done to bring this close to here is actually equal to k q dq over r, okay? And this is very close or equivalent to the previous expression that we derived, which was k q1 q2 over r. We were assuming here point charges, We're going to assume also here point charge because this dq is very small. Okay. So this is k q dq over r. So let's find. Let me think for a moment. Yes. And now, so the work done here, it's and also this initial Q, this can be written as rho times 4 pi 4 over 3 pi r cubed. There's the Q that was there. The Q that we are adding is 4 pi r squared dr. This whole thing is divided over r. And in order, so we see here a dr term. Okay? This is the dr term. If we integrate these both expressions, we are going to get the energy. So this u is equal to the k q1 times dq. This is small r. If we integrate over r, we can find the total energy of the system. Okay? And we are defining here that the charge itself is equal to the rho, which is the charge density of the system, which is measured in coulombs per meter cube, times d volume or volume, which is another meter cube. Okay? So this is how we have to deal with the analysis of the fields which are created for charge distribution. Now, being able to write these integrals, it might be sometimes difficult, but it's also a very good exercise to use to apply the knowledge that you learn from calculus. So, this was one example. Let's look at another example. Let's assume that we have a thread which has some charge density. And since this is a single line, we define the charge density as lambda, which is measured in coulombs per meter. Okay? And then, if this is coulomb per meter, we want to find, and let's assume that this is an infinitely long line. We want to find the electric field at some point here. And the distance, let's assume this distance to be r, distance r. So then all we do is that the language that we use is this. We assume that this is the point 0, and we say the following. This is something that you can memorize, and like a song, you say that at any distance z, I select an infinitesimally small element dz. Okay? That was the song. Okay. So what was the song here? We say at any radius r, we extend an object which is thick dr. Okay, that's the song that we do when you have a volume. That's what we say when you have a line component or line. The charges which are extended in space like a line. Okay? Here, in the previous example, where the charge is extended in space over volume. So, at any distance z, we selected dz. Good. This is a generalized term, and later on, when we do this integral, where the z is, we will do this. Okay? So we will integrate from minus infinity to plus infinity to cover all of it. But that's good. So let's move on. That's the first thing. The second thing that we do is that we find the infinitesimally small dE, electric field. It's a vector. What is the infinitesimally small electric field? This is K dq. So let's see here. What is the infinitesimally small charge dq? dq, it's already written in the board. It's equal to lambda times dz. Okay? Lambda is the charge density, dz is the infinitesimally small element. Good. We know the dq. Then we can use the expression E is equal to K Q over R squared. That's the expression. Let's do it here. K. Instead of Q, we're at dq, so this is lambda dz over R squared. What is R squared? Is this distance squared, which is equal to R squared, actually when I say R squared, let's consider this one to be L, constant value. This will be L squared plus Z squared, like Pythagorean theorem. This is a 90-degree angle, that's L squared plus Z squared, we get the hypotenuse R squared. So this is the electric field. And this electric field, it's this. We show it like this. But probably this is not all the thing, because since this extends from plus infinity to minus infinity, most probably we also have here symmetric charge density, which extends like this. And this creates an electric field like this. And we know that electric fields are vector quantities, so for any component in black, we get also another component. And it looks like because of the symmetry, these two will cancel each other, because vectors with opposite directions, they do cancel each other. So the only surviving terms is going to be the x component, if we assume that this is the x-axis. So then, this dE along the x, we can write this as dE times cosine x. So let this be angle theta, this is angle theta. We do here cosine theta. So if this is here cosine theta, what is the cosine theta from here? Cosine theta, it can be defined as this side, this adjacent side, ring and jigger, the simple hypotenuse divided by the hypotenuse. So this whole thing, this is equal to dE we get from the expression above. So we get this here, A lambda dz divided by L squared plus Z squared times the cosine. Cosine is L divided by the square root of L squared plus Z squared. So this is the dE, and this is the moment that we need to integrate both sides of the equation from minus infinity to plus infinity, and that will be the electric field for this infinitesimally long extended piece of wire. And then I guess we can easily determine some terms that we can take them out of the integral, because these are constants. But inside the integral, we're left with this k lambda L, and then here we have the dz divided by a constant L squared plus Z squared to the power 3 over 2. Okay. Now, to take this integral, this is a table integral. You just search for some formulas that you can on a cheat sheet or formula sheets on calculus courses. Let me see if I have it somewhere. Probably I don't remember it myself. It's not something that we can. We don't memorize this one very easily, but similarly to using this expression, we can also use Gauss Law. I'm sure that you know Gauss Law by now, but the Gauss Law, we derived it before a moment. So the Gauss Law, it stated that the flux of E ds, this was equal to Q over epsilon 0. Now, this Q, we call this one enclosed charge. So we have Gauss Law. First, we determine closed volume, okay? So the enclosed volume, if we have such a wire, because of the symmetry, we can assume a cylinder, okay? So this is the closed volume. Then we can find the electric field, or we find all this. We determine all the surfaces. We have surface 1, surface 2, and surface 3 at the bottom. So this enclosed volume, it has 3 surfaces. Then we look at the electric field lines. Electric field, they go like this. And the total flux This is equal to the flux over surface 1 plus flux over surface 2 plus flux over surface 3. So if we add these three, we can notice that the flux over the surface 1 is equal to 0 because the surface area element is perpendicular here. It's like this here. So in red, we have shown the three surface area vectors which determine the different areas. And we see, and in black, we show the direction of the electric fields. This was a mistake. The electric field, even at the surface area, is like this. So it can be easy for us to see that the flux over surface area 1 and over surface area 3, they are 0. We are left only with flux 2. Flux 2 it's equal to the electric field times. So what is the surface area of a cylinder? The surface area of a cylinder is this. So this is the cylinder, and what is the outer surface area that we want to consider? It's, if you open this up, this is this side times this side. So if this is if this one has a certain radius, specific radius, then this perimeter is going to be equal to 2 pi r. This is 2 pi r times the length of interest. So this, let's assign this to be length L, which we define this one as length L. For length L here, actually, since the L here, we consider the radius. Let's assume that the radius of this one is L, 2 pi L. It's not the best notation probably. And this area here, let's call this one side, Greek side. And then, so the flux is electric field times area. Let's look at the units. These two are measured in meters squared. This whole thing, it's equal to the enclosed charge. The enclosed charge, it's equal to lambda times the length of this thing, and that's all that we need. Because the Gauss Law, it states that EBS, this is equal to Q enclosed over epsilon 0. Sorry, I forgot that epsilon 0 here. So if, in this case, we just cancel out similar terms, and we are left with the electric field to be equal to lambda over 2 pi epsilon 0, 1 over L. Okay, so this is the electric field, which is extended from the charge density, which could be like a line, and it looks like the electric field is proportional to 1 over the distance. So for a moment, let's look at let's think about in this way. Let me look at some area which I can erase. Let me take this out. Now this integral, which we did not conclude, this integral, if you do this one, you get the same result. So these two are equal. Now, let's assume for a moment, if you have a point charge, let's consider what is the dimension of a point charge. Probably a point charge, the dimension is 0. You know that in linear algebra, you have considered that the null space has dimension of we took by definition something, but for a moment, let's assume dimension is equal to 0 for a point charge, and the electric field is proportional to 1 over r squared. Now, if a line, it has a dimension of 1, which, like in this case, the electric field is proportional to 1 over r. Okay, that's what we found here. So the electric field is proportional to 1 over meter, like in this here. Now, if we have the dimension of a charge density is like 2, the electric field is proportional to 1. So this is proportional to r to the power m. And m is -2. This is also proportional to r over m when m is equal to -1. And in 2D, what would you expect the m to be? Can I have an answer from you? So, could you expect any straightforward relationship? Can I have just someone guess a number from you? It also gives me a sense that you are at least one is on duty to answer my questions. Sa mund tjetë kjo mëja? Mund të marrë një përgjigje? So,
Profesor, po nëse ishte me +1, se cila në veti jetë 0.
Po, nëse përdorim kështu logjik kaq elementare, ose no offense, kjo mund të jetë diçka 0, por i bie dikush për ju që mund të jetë i interesuar për modelet të kësaj natyre, i takon që çfarë i takon? Që ta kemi një relacion që d-ja d për -1, i takon që kjo m-ja minus dimensioni është konstante. Kjo që ka një relacion. Po shikojmë sa e vërtet mund të jetë kjo në fakt. Ty Kristina të je rehat për thukë të gjë që kjo mund të jetë 0?
Tani unë thash duke parë si lëvizën ato numrat e tjerë, po si ndryshon m-ja, po.
Në rregull, ke drejtë, ke shumë të drejtë. Tani çështja që diskutuam që sapo zgjidhem më përpara është një tet i cili ka një ngarkesë, ka këtë formë, se ky është një-dimensional. Rasti tjetër që mund të konsiderojmë është kjo copa letrës. Kjo copa letrës kjo është 2D. Nuk ka vëllim, nuk është 3D, është shumë e hollë. Ka vëllim, por vëllimin e ka trashësinë e ka delta x. Okej? Pra, nëse vëllimi trashësia e kësaj është delta x, do të thotë që e ka 0. So it's well defined in space. Delta functions, I'm sure that you have seen this in other courses, but we can solve this problem very fast. So let's allow me to erase this part, and let's have a piece of paper which extends like this, okay? So you are looking at this piece of paper which extends like this, and this has a charge density. Let's assign this one sigma, which is Coulomb divided by meter squared, okay? Here it was Coulomb per meter, now it's Coulomb per meter squared, and let's try to identify a surface area or a volume to have a Gaussian surface. In order to do this, you can assume the following. So if this is an infinitesimally large surface area, we can assume like a cylinder. That's how a cylinder looks like, and we can cut it like this from this side and like this from this side, which means that we can have a surface area here, which extends like, and also here. And in this case, we also have 3 surface areas of interest. We have surface area 1, right? Surface area 2, and surface area 3. But be aware, these are the surface areas over which we are going to calculate the flux. Now, in red, let me draw in red the vectors which define the surface areas. Okay, so this is pointing out this way, and here we get this. In red, we have because we need to calculate EDS. So this DS, probably I draw this in red so that we know what we do the color coding explanation. The electric field, if this is an infinitesimally large charge distribution, the electric field is going to always point outwards. Okay, so it points in this direction or in this direction. So if we are to draw them here, this is this way, on this surface is this way, on this surface is this way. If these are the directions of the surface area in red and of the electric field in black, then we can say that the flux is equal to flux 1 plus flux 2 plus flux 3. Okay? On which surface area the flux is 0? To where is the flux equal to 0? The flux equal to 0 is going to be here over flux 2. Okay? And then let's assume that this area here is A. okay? And also on the piece of paper, the amount of charge that is enclosed is equal to, so that the Q is going to be equal to this sigma times A, because this is the enclosed charge, right? So then this is going to be equal to the flux itself, it's E times A on this side, okay, plus E times A on this other side. Would you agree with this part? Then this whole thing, so the flux itself, it looks like it's 2EA. And this whole thing it should be equal to Q enclosed over epsilon 0. So let's look at this expression here. So Q enclosed is sigma times A divided by epsilon 0. That's it. So if this is the case, we can cancel out similar terms, these areas, and it looks like the electric field is sigma over 2 epsilon 0. So this is really we have no distance. So this is R to the power 0. So apparently this was correct, but we could also derive this one. So it looks like for a two-dimensional structure, this was for 1D, but for 2D, electric field is equal to sigma over 2 epsilon 0. But this is for infinitesimally large surface charge distribution, or charge distribution over surface area. And this is sigma over 2 epsilon 0. So now we are in chapter 3 of the textbook. And our objective, it was to have a complete analysis of electrostatics starting from the two postulates. Now, allow me to erase some parts here, and I hope this was clear, most of it. I thank you for your inputs. But before, so we started with a postulate which looked like this. The divergence of E, this was equal to rho over epsilon 0, and the curl of E, this was simply equal to 0. This is the differential form of the two postulates. The same, we have also the integral form, which is the EPS. This is equal to Q over epsilon 0, and the other law is EDL. This is equal to 0. So if you look at these, they say the same thing, okay? But we start with this, and we got, how do we get this? We get this by applying the divergence theorem, okay? With the divergence theorem, we get this here, we apply the Stokes Theorem, we apply Stokes, and we get this. And how do we apply the Stokes Theorem? We integrate this one over surface area, right? On the other side, we should get the integral over line, like this. So this is what we get for the electrostatics. We start with this, we did a couple of examples, and the next thing which follows also the textbook, or the path that we're going to follow, is we analyze the electric fields and the potentials for extended charge densities, okay, over surface area or over volume. And after that, we're going to discuss the electric field in materials. Okay, and when we study the electric field in materials, we are not dealing anymore with the permittivity. So the permittivity, it will be a new quantity, which is going to be epsilon r times epsilon 0. This would be permittivity inside the material, and a piece of material can be a piece of wood or a piece of plastic. And here, I can ask you this: what is the unit of epsilon r? Can I get an answer from you? So what is the unit of epsilon r? Well, the unit should be 0. No, sorry, it has no units. It doesn't mean that's a mistake, because this is permittivity, and this is also permittivity. Material, vacuum, so the unit should be the same on both sides, which means that this is just a number. Okay? This is a coefficient. The relative permittivity, it's just a number. And when we analyze the forces or the electric fields in different materials, we're going to have to define a new quantity, which is or an electric field flux, which is the D. So we're going to define this D vector, but probably we won't start it today. And in order to have this quantity, we should also define some effects which happen inside the material if we have an external electric field. And we have similar phenomena in magnetism and in electrostatic fields. So the coupling. So we have, this is called a dipole. But this one, we will explain this one next time. So the dipole is a microscopic quantity which is defined as two charges which are very close to each other, and the one is positive, one is negative. Okay, even a capacitor, it's a dipole because it has one positive piece of metal and one negative piece of metal, which stand at a certain distance. They should not touch each other. So this dipole is a microscopic picture of how this is constructed in detail. We have a quantity which is defined as QD. So that's a dipole moment. But then this is microscopic picture, small microscopic picture. And then in the macro scale, if we add up all of these, or the density of this quantity, we define a new quantity which is called the polarization vector. Okay? So on every material, or on most of the materials, if they are inserted inside of an electric field, the polarization vector P will arise, and then once this polarization vector P arises, we're going to have a new quantity, which is the displacement vector, the D, which is equal to epsilon E plus P. Okay, so we'll get this new quantity. And then, of course, this D is also a vector. This behaves also to many of these laws. But if you look at a similarity between these two, some of you might observe that if we multiply both sides of the equation, here with epsilon and here with, it's not epsilon, with permittivity, this might cancel out, and probably you might be expecting that the divergence of D is just equal to rho. Okay? The divergence of D, this is equal to rho. Of course, we're going to cover this one in detail, but for now, I think that your task until next time is to go over chapter 3 and to have a look at the examples. And next time we'll start the electric field in materials. Do you have any questions so far? I mean, for this so far during the whole session? Any question?
Profesor, kisha një pyetje, po jo për këtë të sotme.
Patjetër, po.
Ka të bëjë me atë vërtetimin e Divergence Theorem për cilindër.
Shumë mirë, po.
Nuk e di nëse që kam parë shembuj të librit, po nuk është se më kanë dalë fiksi përgjigjet. Edhe nuk e di si merret vektori DS për sipërfaqen anësore. Unë kam marrë AR. Dhe për ato bazat.
Shumë mirë. Kende i ushtrim ato ta mendojmë. Divergence Theorem për cilindrin, Okay, let's try to look at it together. So Divergence Theorem, first of all, është kështu apo jo? Divergjenca e vektorit A, po quhet A, integralin e vëllim, kjo është i barabartë me, në fakt sa quhet E, kjo është A herë surface area. Por integrali surface area është integrali mbyllur. Po, dhe çfarë paqartë ka këtu, Kristina?
Tani në fakt unë studioj tre kështu sipërfaqen anësore, sipërfaqen e bazës sipërme dhe atë të poshtmen.
Po, shumë drejt. Po.
Tani për atë të sipërmen si vektor pingun marr AZ-n.
Po, shumë drejt. Nëse sistemi koordinativ marrim kështu, ke drejt, po.
Për bazën e poshtme marr minus AZ.
Shumë drejt, po, minus AZ, po.
E për sipërfaqen kështu, për sipërfaqen anësore marr AR-n. Nuk e di sa e saktë është kjo.
Shumë drejt, është AR e vogël, nëse përdorim terminologjinë e cilindrike që themi R phi dhe z. Po, shumë mirë, në rregull ke, po.
Jo thjesht desha konfirmim nga që e kam zgjidhur një ushtrim edhe nuk është se më ka dalë kështu fiksi përgjigjja, se libri ka dhe përgjigje për sa shembuj.
Shumë mirë,
E tash mos ndoshta i kam marrë unë gabim këto, do thonë vektor pingull.
Po ja për shumë ta ndjekim pak këtë, për shumë ndoshta mund të mbash shënim në kohë që flasim, po mundon bëj të gjë. Sa është kjo vëllimi vetë çfarë është? dv në të koordinata cilindrike, për shumë kjo e ka dr. Po kjo koordinata sa e ka grafia?
Është r dë phi.
R dë phi, shumë të drejtë. Nëse do të kjo është dz.
Po.
Pra kjo do vogël, ne mund ta shkruajmë direkt dr dë phi dz. Tani kjo sipërfaqe që po mendojmë ne, ti po atëherë po mendon presinat të kapë sipërfaqe këtu apo?
Po.
Në kjo sipërfaqe jashtme që ka rënë konstante. Nëse ka rënë konstante, kjo ds-ja, atë ka dalë kjo ds aty, që përdor r dë phi dz. A ke përdorur këtë si ds?
Në fakt ka qenë kështu ar. Po, tani po.
Ke përdorur këtë apo?
Po, thjesht e shënoj ar-ën, e shënoj në fillimun.
Okej.
Është po.
Në rregull, dakor. Po nëse kjo është situata, për shembull, çfarë fushë ke pasur apo për shembull, me këtë që shkruajmë tani është pak më shumë e qartë apo çfarë?
Po jo, thjesht kështu i kam bërë dhe unë këta, kam shumëzuar pastaj, ca gjëra anullohen, që dalin 0, edhe i kam mbledhur. Domethënë, kam bërë integralit për të treja pjesët. Në fund i kam mbledhur, po nëse mbase s'më ka dalë rezultati kështu njësoj, mbase kam bërë një gabim kështu në kalkulim, po thjesht do të sigurohesha që vektorët janë okay.
Po te libri që ta shikoj edhe unë.
Është tek mësimi që është Divergence Theorem. Është një shembull me cilindër, është i pazgjidhur. Është po ai mësimi. Domethënë është ai ushtrimi me kështu me kub që kemi bërë ne. E pak më poshtë është një me cilindër.
Shumë mirë. Atëherë më lejo ta shikojmë direkt nga libri, se kam librin këtu.
Po pa ju Marko.
Librin faqen e gjendot aty te çfarë faqe është në libër? The Divergence Theorem, thamë ne, po ta gjejmë tani herë. Spherical coordinate system. Mos është faqja të 52?
Po më duket, po. Është exercise 2.12.
Pika C atë bie, verify the divergence theorem.
Po.
Në rregull, bëjmë ta mundojmë pak, ndoshta nuk e zgjidhim dot deri në fund, po të shikojmë deri fare pike. Pra vektori që duhet të konsiderojmë ne që ka sa është ajo? Është r ARR, okay. Që është ARR plus AZZ, okay. Për që ka një fushë vektoriale e cila ndërkohë që në rritë r-ja, rritet dhe për që ka diçka që rritet linearisht me r dhe linearisht me z. Pra sa më shumë që ndjiteni dakord. Kjo që nga a-ja, kjo thot çfarë sipërfaqe ka? Find the total outward flux over circular cylinder around the z-axis. Rrezën e ka 2, lartësinë e ka 4. Shumë mirë, rrezën 2, lartësinë e ka 4. Atëherë, kjo është 4 këtu, rrezja është 2. Atëherë, do kemi 2 bukur.
Është pa kamerë të lutem?
Patjetër. Okay, më fali. Tani duhet të lexoj pak monitorin tim. Por i takon që nëse kjo është konfigurimi që kemi, vektorin besoj kam shkruar të saktun, rrezja 2, kjo 4. Divergence Theorem. Okej, vazhdojmë atëherë. Nëse kjo është situata, x pari për Divergence Theorem ti gjejmë të divergence. Sa është kjo divergence term? Sa është gjejmë të what is the divergence of A? Në koordinata cilindrike, si e kemi shkruar në këtë? A gjeni dot, për shembull, ju lutem, nëse edhe ju mund të doni ta gjeni tek libri, Po ti
Profesor, ajo
zëvullu,
është kështu, a thon gradienti vetë si formul,
po,
është AR, që shumëzon D për mbi DR,
arë, të përmbi dërë, po,
plus kështu afi, po,
po,
D për mbi R dëfi,
po, kështu.
plus AZ D për mbi DZ.
Ok, më ndihmoni pak të këtë pjesë, plus, sa të shqipa këto, plus AZ, D përmbi DZ. Pra, kjo është del operator, ky i gjithë të shumëzohet me ARR, plus AZZ. Në qoftë se deri këtu jemi njësoj, atëherë ne do marrim dot product, vetë tërë që na mbjetojnë është AR me AR, del njësh, dhe na del DR për mbi R. Dakor, kjo pjesa e parë. Pastaj pjesa tjetër, a shikoni dot gjithë drasën me të kuqe? Pjesa tjetër, pastaj kemi AZ, do shumëzoj AZ, dhe kemi DZ plus DZ për mbi Z. Çfarë na del kjo rezultati këtu? A jemi dakord që del dysh? Jemi në rregull? Pra në del që divergjenca e kësaj del dysh. Pra po ti ke shprehje këtu, ne kemi integrali i dyshit, që është konstant, mund dalë jashtë dv. Më dëgjoni? Nëse kjo del kështu, sa është vëllimi vet, pra kjo del konstant jashtë, vëllimi këtu është i barabartë me pi katror herë lartësi. Pi katror herë lartësi, i bie pi është pi, rreza ishte 2 herë 4, lartësia është rreza ishte 2 në katror, është 4 herë 4, pra dit 16 pi apo. 16 pi është vëllimi, herë 2, kjo del 32 pi. Ka dalë kështu, Kristina?
Po profesor, mua aq më ka dalë, po të librin më duket se është përgjigje 48.
Libri sa e ka raportuar këtë zgjidhje?
48.
Për ta mendoj pak, pse vallë 48 pi. Ndoshta prit, si mund ta 48 pi, si del 24, si mund ta zgjidhni 24 që ajo? Dyshim besoj kemi të saktë. Dyshi është saktë. Kjo shumëzon 2. Qofse aty ka dalë 48 pi, prisim për 2, do dalë 24 pi. 24 pi lartësia është 4, jo s'ka shans. Këtë mendoj që keni saktë këtë dyshin.
O profesor, nëse është 3 ajo, atëherë del 48.
Po 3, po vektori është thjesht AR, për ta mendojmë pak. Kjo është apo shoh saktë, kjo është AR herë AZ herë Z.
A nuk duhet shumëzuar me 1 over H1, H2, H3 edhe H1, H2, H3 e kësaj është 1 për mbi R, më duhet, sa i bie?
Shikoni, kjo del operator, kjo në koordinata cilindrike, ma gjeni do çfarë faqe të librit është për ta gjenë pak. Del operator në cylindrical coordinate system, sa ta gjejmë pak këtu. Një sekund. Cylindrical, del operator, atëherë këtu e kemi gabimin duket. Delta A phi AZ AR, kjo është R, kjo është gabimi, po. Kjo është 1 për mbi R. Del operator, se këtu është gabimi jonë atëherë, del operator me A, ky vetë është barabartë
po shohim.
Që unë po referohem librit tani, po shikoj drejt nga libri, pra kjo është barabartë me 1 për mbi R, që shumëzon derivatin me R.
Profesor, unë e kamerën, të lutem.
Yes, pra, unë duke referuar librit, më lejon edhe të shikoj një gjë të vogël këtu. Herën e kaluar, ne shkruajtëm shprehjen e përgjithshme në dras dhe derivuam duke marrë ato permitivitetet 1, 2, 3, nëse mbani mend, nëse shikoni edhe videon, por të ndjek këtë formulën këtu, kjo është D për mbi R, R herë AR. Kjo është R herë AR plus 1 për mbi R, kjo qëndron në një në fakt, 1 për mbi R, delta për mbi A phi për mbi phi plus delta AZ përmbi Z. Delta AZ përmbi delta Z. Pra, del operator, që shumëton vektorin në koordinata cilindrike, kjo është gabim, kjo është e saktë. Atëherë, besoj kjo shpreha duket mirë në video. Okej. Për shembull, nga kjo shprehje këtu, R-ja është R. Pra këtu lejoni ky është gabimi jonë në bashkë, që shumëton R. A-fia është 0. Në rregull, e përdorëm kështu, kjo është 0. AZ-i është 0. AZ-i është 0. Bukur. Atëherë këtu vazhdojmë. Këtu çfarë kemi? Kjo është R katror. Derivati R katrorit sa del? Sa është derivati R katrorit?
2R.
Është 2R. Pra kjo që shumëzon 1 përmbi R që shumëzon 2R plus 0 plus kjo del 0, kjo del derivati Z, në Z plus 1. Pra kjo është e barabartë me R thjeshtohen 2 plus 1 3. Atëherë e gjetëm kush gabimi. I bie kjo është 3. Pra kjo dyshi këtu, ta kthej pak videon aty ku e kishim. A jemi të qartë tani se dyshi u bë 3?
Po, profesor.
Divergjenca është 3. Kjo është divergjenca dhe 3 dv, pra i bie herë 16 pi dhe 49 pi. Në rregull. Pra këtë pjesën e rregulluam. Në rregull? Atëherë nëse kjo është e saktë, kjo nuk ka ndonjë më shumë të rëndësishëm, kjo shpreha ky ishte gabim që shkruajmë nga e parë. Kjo është e saktë, kjo është e saktë deri 3. Atëherë vazhdojmë. Çfarë do të gjejmë? Do të gjejmë ADS. Do kam sipërfaqen e parë. Sipërfaqja e parë kapim këtu poshtë. Kjo këtu poshtë, nëse është vendosur surface area 1. Sa është, prita mendoj për një moment, sa është vektori A këtu poshtë? A-ja këtu poshtë e ka zën 0. A-ja e surface 1 është e barabartë me R, kjo shumëzon R. Dakor, kjo është A-ja. Në sipërfaqen e dytë që është ansore, çfarë kemi ne? A-ja si vektor është i barabartë me R-ja. Sa është R-ja në sipërfaqen e jashtme të kësaj? R-ja është 2, se ishte që rrezi ishte 2, atëherë këne dele 2R, në rregull, plus AZ herë Z. Z-i nga që është variabël, do e mbajmë siç është, pra dhe për plus Z që shumëzon AZ. Në sipërfaqen e tretë, vektori A, jemi këtu lart fare, është e barabartë me rrezja është variabël, pra rrezja nuk është konstante, do e mbajmë siç është, A-ja është e barabartë me R herë AR, nuk ka ndryshim se e kemi shkruar këtu, plus Z-i është 4, ka që lartësia është 4, këtë dhe plus 4 AZ. Pra, kjo është vektori me 3 sipërfaqe. Kjo në rregull, atëherë çfarë do të bëjmë tjetër ne? Duhet të gjejmë
Profesor, po rrezja, pse është variabël? Rrezja është cilindër. Nuk do të jetë rrezja është njësoj.
Ke të drejtë, por ne na intereson të kjo sipërfaqe këtu lart. Është njësoj, por ne do integrojmë mbi një sipërfaqe që R-ja ndryshon. Pra kur të integrojmë me DS, që është surface area element, po sipërfaqja është e ka rënë variabël, nuk e mbajmë të rënë konstante. Për shembull, pse? Nga që pritani të orientohet pak. Këtu, nëse ecim në pikat e ndryshme në këtë sipërfaqe, çfarë ka konstante gjithë këtë sipërfaqe? Ka vetëm Z-in, është 4.
Po.
Jemi dakord? Kurse R-ja është R. Ta bën sa është R këtu nuk e themi dot. Te kjo sipërfaqe këtu sa është R-ja? Kjo pika këtu e ka ndryshme me këtë pikën, ose me këtë cepi, skajet e kanë 4, në fakt 2 R. Po jo kjo qendër, kjo ka 0 këtu. Kjo pika në mesfare.
Po, kuptoj.
Në rregull, pra nëse jeni në rregull deri në këtë pikë, këtë A, sipërfaqja poshtë, kjo është A-ja sipërfaqja e jashtme, në sipërfaqen e jashtme argumentuam që R-ja është 2, kjo është tjetër në rregull. Atëherë i gjetëm A. Ai, pra A, mos harrojmë që Divergence Theorem është kjo. A në gjetëm, për 3 sipërfaqe gjem DS-n. Sa është DS-ja këtu poshtë? DS-ja poshtë, ta bëjmë me të Z-s. DS-ja është vektor dhe drejtimin e ka minus AZ. Pra kjo DS-ja vetë është DS që shumëton çfarë? Jemi dakord që është minus AZ?
Po, ashtu po, minus AZ, po.
Në rregull. Në fakt, DS-ja vetë çfarë është? Çfarë është DS-ja në këto lloj koordinatash? Unë mendoj, ndoshta më ta shkruaj të poshtë, se po e përdorim këtu për gjëra që i fshim. DS-ja në sistemin cilindrike, unë mendoj që mund të shkruhet si 2πr që shumëzon dr. Kjo është një DS shumë e përshtatshme, sepse çfarë mund të bëjmë? R po ta marrim nga 0-ja deri ku është maksimale, ne po e mendojmë që këtu our infinitesimally small surface area element janë këto. Kuptoni, pra, po shikoni një byrek me rroda kështu, po shikoni nga lart në byrekun që është bërë me rroda, sa e ka perimetrin kjo? Është 2πr shumëzim për trashësim. Po mirë, në këtë DS mund ta shkruajmë këtu, por të bëj një pyetje, sa është dot product midis kësaj A-së dhe kësaj DS-s?
Është 0.
Për 0, iku. Pra, nuk ka nevojë ta llogarisë fare, iku kjo. Shikojmë këtu tani. Kjo kemi surface area element për gjatë kësaj në pjesën e jashtëm. Sa është DS-ja? Atë është DS. DS-ja në krahun e jashtëm në sistemin koordinativ cilindrik, se e fshiva dv, çfarë do të jetë kjo? Kjo do të jetë barabartë me
Është me AR, se do të thonë rrezja është shumë dalse.
po, është e drejtë, është AR, që shumëzon R d phi, që shumëzon dz. Jemi dakord?
Po.
Në rregull. Këtë e shkruajmë ne, ndërkohë, te sipërfaqe poshtë fare, sa është DS-ja? DS-ja është e barabartë AZ-i është AZ, kjo nuk ndryshon, që shumëzon, atëherë të shumë të 2πr dr. Jemi dakord? Me ta mendoj pak. Po. Kjo është 2πr dr. Jemi në rregull deri te kjo pjesa? Tani, ndërkohë që kemi këto, unë po mendoj, po i shumëzoj kështu tek e tek. Kjo shumëzimi i parë del 0, kjo s'po e marrim. Te e dyta, po të marrim dot produkt të AS me DS, mendoj që kjo AZ-i na iket. Jemi dakord se vetëm kjo është non zero. Shumë e faleminderit për konfirmimin, i bie që kjo do kemi të bëjmë me 2r, pra po kemi të integratin këtu, ADS-ja, po shkruaj këtë integratin në rastin e dytë këtu, kemi 2r d phi dz, d phi, një sekundë, nuk po bind, kam diçka s'po bindem do të d phi dz, kjo në rregull. Kemi këtë, dhe në rastin e tretë, tu kemi të bëjmë me A-ja shumëzon AZ-in, dhe prapë do na ngjelet 4 herë 2π, në rregull, 4 herë 2π r/r. Dakor? Edhe kjo ka integralin të sipërfaqe tjetër. Tani, nga kjo pika, nëse ju e vazhdoni, nëse mendoni edhe 5 minutë tjetër, shikoni rezultatin, nëse nuk e zgjidhni, mund ta diskutojmë përsëri, në rregull?
Po, profesor, nuk i deri këtu mirë. Ajo që s'kuptoj unë tek numri 3,
Po.
tek DS-ja, unë se kuptoj, më thëmë pse kemi bërë kështu. Okej, AZ-i mirë, se ajo është pingulje. Po e pjesa 2π r dr, se vetëm sa kam parë te libri.
Po.
DS-ja është, domthonë vektori pingull me sipërfaqen që marrin, dhe pjesa që shumëzon pjesën që mbetet nga ajo vëllimi, dv-ja që është shënuar du. Ajo është më tepër për kollaj, po për momentin te vëllimi, nga që është kështu sipërfaqe cilindrike, nuk e kuptoj pse del 2π r dr.
Se del kjo këtu.
Po.
Po për shembull ne ta mendojmë kështu. Sa është ne të më dha sipërfaqen këtu, dakor? Është kjo sipërfaqe. Kjo si mund ta gjejmë sipërfaqen e gjithë thirrjetit? Ajo që mund të bëjmë ne është të marrim këto sipërfaqe të vogla. Dakor? Edhe sipërfaqja totale e rrjetit është e barabartë me integralin e DS-s. Jemi dakord me këtë pjesë?
Po.
Shumë mirë. Këtu atëherë çfarë kemi DS-t? DS-t janë barabartë me 2πr dr. Edhe a jemi dakord nëse në këtë është si puna merr një kokë qep, përpret qepën mes, po ta shikoj sipërfaqen e qepës është përbërë nga kështu, sa e trash është çdo shtresë e qepës, ashtu e më kupton si
Po, kuptoj.
po edhe këtu, po të integrojmë këtu, 2 pi është konstante deri jashtë, 2 pi është konstante, r dr, sa është integrali r dr-s?
R4/2.
R4/2, 2 shatikin, r-ja do integrojmë nga 0 te r-ja e madhe. Sa na del neve? Me pi r4. A është kjo sipërfaqja e rrethit?
Po.
S'duket ndoshta. Pra, a jemi të bindur që kjo që nga sipërfaqja e përshtatshme? Pra, nëse kjo është DS-ja, po ta integrojmë, që do të thotë po të mbledhim këto trashësi të kësaj natyre, do na dalë kështu. Ne mund ta bëjmë edhe ndryshe, po është pak më vështirë. Pra, jemi të bindur pse na doli kjo këtu? Përveç kësaj, ne mund të bëjmë gjë. Këtë sferë këtu, mund të kishim marrë sistem koordinativ XY dhe do ishte kështu. Mund të kishim integruar këto lloj copash. Kjo copa sa është sipërfaqja e kësaj? Sipërfaqja e kësaj është kjo dx-i, në rregull? Pra ds-ja këtu është e barabartë me dx, që është lartësia e kësaj, shumësim lartësinë. Sa është lartësia e kësaj? Lartësia e kësaj është y, kurse y-i është rrezja r në katror minus x në katror r në katrore. Jemi dakord? Por kjo është goxha më komplekse. Te këtë sipërfaqe të gjithën, o do e shkruajmë si kështu në këtë në seksionet e cilat do integrojmë nga minus r-ja tek r-ja përgjatë x-it, në rregull, ose do i marrim në këtë formë, këtë me të kuqe, do integrojmë përgjatë y-it, ose kështu. Mu më duket, mendoj se
kjo është mënyra e parë.
Ë?
Është më thjesht kjo mënyra me 2 pi r dr.
Mendoj se po, 2 pi r dr është më e lehtë. Ashtu siç është më e lehtë, për shembull, për gjetur vëllimin e një sfere. Si e gjejmë vëllimin e një sfere? Vëllimin e sferës ne mund ta konsiderojmë sikur po integrojmë lëkurat e portokallit ose lëkurat e qepës. Marrim një qep edhe fillojmë me heqje me të lëkurat copa. Sa është dv-ja? Dv-ja është 4 pi r katror dr. Dakor? Kjo është, si më thënë, vëllimi i lëkurës portokallit ose vëllimi i lëkurës së mollës. Atëherë vëllimi total me sa është barabartë integrali i kësaj, dhe po të integrojmë 4 pi r, për shembull, po të integrojmë në 2 krahat e ekuacionit. E integrojmë. Kështu sa është integrali r katror dr? Integrali r katror dr, kjo është konstante, është r kund të tretave. A është ky vëllimi i sferës? Pasi e gjetëm, sipërfaqja e topit të futbollit ose portokallit, shumësim për trasinë e lëkurës portokallit, kjo është, në tip ky vëllim. Edhe këtu pastaj, kur vim te kjo pjesa tjetër, deri kjo, është pak më e qartë?
Po, profesor, faleminderit.
Atëherë, këtu që i lamë i bie detyrë shtëpie, kemi pak ta shikoni pak, ta zhvilloni deri në fund të pjesën, duke pas parasysh që vektori A në këto tre sipërfaqe ka këtë formë, DS-t janë këto, dot product strukturë janë këto, tani bie gjeni pak sa del rezultati. Ta bëni në shpikët ta diskutojmë vend tjetër?
Po, profesor, patjetër.
Ndonjë pyetje tjetër që mund të keni? Në rregull, nëse keni pyetje mund ta mbyllim për sot. Detyrat ju keni dorëzuar, atë zgjedhjet e detyrave do e postojmë në Google Classroom dhe për çdo gjë tjetër që mund të keni mund të komunikojmë përsëri me emailin. Atëherë për sot po e mbyllim. Ju faleminderit për pyetjen shumë. Atëherë gjithë mirët.
Faleminderit profesor, pafshim.
Pafshim.